Hello, in this video we shall be looking at Hooke's law. Now, if a material, say a wire, is put under, well, it has a load attached to it, a load, then it will feel a force pulling down it, if you like, a tension. Okay. Now, the material may in fact stretch a little, and if it stretches a little it will extend. So if this is the original length there and it's the loads put on, and if it's made to extend a little bit more like that, that is known as the extension. X or in some syllabuses the letter is for extension is E. Okay. Now, if you were to plot a graph of the load, now this would be the load, call it, that has to be the load acting down. If you were to plot a graph of your load, which is the force, against the extension, let's call that X, might say load in newtons, perhaps, extension in meters, and again we could use the letter E, then you'll find that if it is a straight line like that, then you're finding that the material, the load against extension, is obeying Hooke's law, and that says that the load, if a load is proportional to the extension, or if you like, the force is proportional to the extension, then Hooke's law is obeyed. And you can form an equation where you can have that force is equal to kx, or sometimes written as force equals ke, where k can stand for the spring constant or the stiffness constant. Okay, now this law is only obeyed up to the limit of proportionality. If a significantly large load is put on, a large tensile stress is put on material, then eventually it would no longer obey Hooke's law. But Hooke's law, up to the limit of proportionality, and when you remove the load, it will go back to its original position again. And a good thing to look at are springs. Springs obey this law very well. Okay, so now, so here's a spring. Okay, let's say that here's a load on the end of it. That's the force going down there. Let's call that, it's a weight there. And perhaps this is how much it has extended, X, or extension E. Now, so there, and as before, plotting force against extension, you get a straight line. So when the load is removed, the spring goes back to its original size. Now, the area under this graph here, okay, this is work has been done stretching the spring, and the energy stored in the spring is known as the strain energy. It can also be known as elastic energy, and the area under the graph within Hooke's law, so its proportional line, you'll find that the work done is equal to the area of that, so that would be half times x times f. Now from Hooke's law, because it's obeying Hooke's law, straight line, you get F equals kx. So substituting that in there, you would get the value of half kx squared. So this is the work done, and this is the energy stored in a spring when it obeys Hooke's law. Now, this stiffness constant, spring constant K, okay. Now, so F equals Kx. Now, if we had, in fact, springs in parallel like that, both of them having both identical springs with the Hooke's law equation F equals Kx, and with the stiffness constant K, and they were both attached, say, to a mass, forming a weight down here, you'd find that effectively the effective stiffness constant it would double. So it would give you the effective value would be 2K. So that'll be the effective value would double it. That's in parallel. Now, if you had two springs in series, again with the same stiffness constant. So again, so F equals Kf. That is the stiffness constant. If they were in series, like this, and this is the weight on the end, W there, you'd find effectively that the spring constant would half. So you would find that the effective spring constant there would be half of half of it would be for simply one spring. Okay.